Hi everyone, my name is Ingao. I'm a senior engineer at the Transportation Technology Center, Inc., TTCI. I started here in 2016 and I'm currently managing the research projects related to railroad cross ties and fastening systems. I'm pleased to present at this symposium and hope everyone can enjoy the presentation. As this title shows here, my presentation topic today is Research of Engineered Polymer Composite Ties at TTCI. In this presentation, I will just use composite ties to refer to engineered polymer composite ties for simplicity. Here's the outline of this presentation. First, I will briefly talk about why the railroad industry wants to use composite ties. Then I will introduce the composite tie test program at TTCI, including both testing at the Facility for Accelerated Service Testing, FAST, and in the revenue service. Then the presentation will be followed by improved design and testing method recommendations developed for composite ties by this test program. Lastly, the key findings and future work will be presented. Cross ties are one of the most expensive assets of a railroad. More than 90% of Class 1 railroad track miles in North America utilize wood ties. However, material wear and the environmental sustainability of wood ties, especially in high rot and high decay areas, lead the railroad interested in alternative cross-tie materials, such as composite ties. Composite ties are made of recycled plastics with ability to resist moisture and abrasion. Therefore, they are expected to extend the tie life in high decay areas. Composite ties are designed to provide one-to-one replacement for wood ties and using the same fastening system and a similar tie dimension. With that motivation, TTCI has been conducting the research on composite tie and fastener systems for more than 20 years. The project is a collaborative research work supported by Association of American Railroads AAR Strategic Research Initiatives Program and the Federal Railroad Administration. The goal is to improve design and testing guidelines for composite ties. A total of 6 types of composite ties have been tested. 2 composite ties designs installed in early 2000s at FAST accumulate 2.1 and 1.7 billion gross tons respectively, before they are removed in 2015. In the 4 years since 2015, another 4 types of composite ties were installed at FAST. Besides the FAST test, 2 revenue service test zones of composite ties were installed at a revenue service territory in 2015. In one location in Nebraska consists of 2 types of composite ties which were installed as panels. The second test in Illinois is intended to investigate composite tie performance when they are interspersed with wood ties. Field inspection and measurements, laboratory testing, as well as numerical modeling are being undertaken to assess the composite tie performance. I will talk in detail in the following slides and summarize the research activities that have been conducted and how these results are driving improvement to recommended practice. First, we explore the loading environment during handling and installation, where the ties could experience a more severe loading condition. We measured the bending stresses in composite ties during a typical installation process and in drop tests to simulate severe loading conditions. Tie remover inserter trip machine was used for tie installation. Simulated drop test was from 4 feet high. The 5 curves in the plot represent the center bending load versus deflection curve for 5 composite tie types. The black dashed line show the peak equivalent center bending loads calculated from these tests. The equivalent center bending load from the ARIMA recommended minimum modulus for rupture, MOR, is also shown for comparison. MOR is a measure of the ultimate bending strength of the tie. As we can see in the plot, maximum bending stresses in composite ties during insertion, nipping, and spiking was higher than the old ARIMA recommended minimum MOR. Dropping composite ties may generate even higher bending stresses. Based on the results, an ARIMA recommended minimum MOR of 2500 psi was proposed, and it has been updated in the ARIMA manual in 2018. Modulus of Elasticity, MOE, is a property that describes the bending stiffness of the tie. The drawing in this slide plots the MOE and MOR for 5 composite tie types, and with 25 ties of each tie type. The green and red markers represent the 2 types of composite ties that last 2.1 and 1.7 billion gross tons at FAST. Tie structural cracking was not observed in either types of the ties. However, other types of composite ties experience some cracking issue even with a higher MOE. Therefore, we believe there's little evidence to suggest that higher MOE is indicative of in-track performance of composite ties. Based on this, the minimum MOE was no longer a recommendation in the older ARIMA manual, and it was replaced with a recommended range in 2018. In-track testing also observed that the environmental decay is minimum on the tie materials for all types of composite ties. In addition, a reduction in plate cutting on composite ties was observed when compared to wood ties. As shown in the photo on the right, the composite tie test zones with ARIMA 14-inch plates installed at FAST in 2000s had less than 1/8 inch high rail plate cutting after 1.7 billion gross tons. For comparison, 3/8 inch plate cutting was observed in a controlled hardwood tie test zone after only 1 billion gross tons. However, there are a couple of failure modes associated with composite ties that are typically not seen on wood ties. Center cracking, which was not observed during installation, has been observed on at least 3 different composite ties in recent testing at FAST. This test at FAST showed about 10% of composite tie experienced center cracking within 200 million gross tons (mgt) of heavy axle load traffic. Spike hole cracking was the other common failure mode observed. Spike hole cracks were generally observed to develop after tonnage accumulation and have not been observed during laboratory spike insertion and pull-out testing. All of these ties meet the ARIMA recommendations of laboratory tests. This indicates that current testing recommendations do not adequately assess the performance of composite ties to address these 2 failure modes. For this reason, we are developing laboratory tests to better address these issues. In the next few slides, I will be focused on the development of a center fatigue to address center cracking issue. As I mentioned earlier, the failure mode is typically not seen on wood ties. The cracking occurs in the center 30-inch of the tie. According to the in-track observation, the center cracking failure often associated with internal voids or defects in the tie center, as you can see in the photos here. Existing laboratory qualification testing in the ARIMA manual has not proven its effectiveness in identifying this failure mode before in-track installation. This highlights the need for a more representative laboratory test. So to get the reasonable inputs for the laboratory test, we conducted field instrumentation on 4 different types of composite ties to quantify the loading environment. We installed strain gauges at the center top surface of ties, and the bending strain data was collected at various train speeds at different times of day and at both fast and revenue service test. The ties in each location were selected by the tensor engineer to ensure severely hanging ties or ties with loose plate were chosen. So overall, these ties were representative of the ties in the test zone. As the plot shows here, the black dashed line represents the measured in-track strain values from fast and revenue service testing. As we can see, the in-track bending loads of composite ties were well below the tie's ultimate bending strength, MOR. Therefore, material fatigue is believed to be the failure mechanism for the observed cracking. This slide shows how we developed the center bending fatigue test to address the center cracking issue from in-track measurement to the final test setup. The bottom left plot here shows an example of the center bending strain data collected at FAST for a certain tie type. As you can see, one bending fatigue cycle is 1 car length, which is measured by the center-to-center of 2 adjacent trucks. The ARIMA Test 6 tie wear abrasion test, which is an existing ARIMA fatigue test on tie and fastening systems, runs at a baseline of 3 million cycles. Each fatigue cycle in Test 6 is 1 truck instead of 1 car. Therefore, to establish a similar traffic volume, 1.5 million cycles was used to fatigue the tie. This is equivalent to approximately 200 mgt of heavy axle load traffic. This slide also shows the test setup on the top right. 4-point bending test setup is used because it can provide a constant moment area to test the tie center area. And the section AD is a 6-inch outer span, which is consistent with the ARIMA 3-point bending test. Section BC is the inner span, which is about 30 inches. Actually, we tested different lengths of inner span. A longer inner span is preferred because it can provide a longer constant moment area for tie testing. However, a longer inner span reduces the length of sections AB and CD. therefore increasing the shear forces in those two areas, and could result in shear failure instead of tie bending failure. We performed the trial tests to use different spans, and during these trial tests, a 30-inch inner span was able to generate the tie center cracks without shear failure. Also considering the fact that most of the in-track center cracking failure was found within the middle 30-inch of tie section, a 30-inch inner span setup was determined to be adequate for this test. In a summary, based on the in-track string measurement and several iterations to develop the test, a 4-point bending test setup is proposed, and the test runs for 1.5 million fatigue cycles or tie failure, whichever comes first. A key function of a tie in ballast track is to provide lateral resistance of track structure. Composite ties should provide a similar or improved lateral track strength to be a practical alternative to wood ties. All composite ties designs generally include some form of surface friction modification, either by stamping or molding of notches or a roughened surface on the sides or bottom of the tie. 3 types of composite ties with different patterns of surface texture were selected for a single tie push test. 2 types of ties had a texturing approximately a 1/4 inch in depth. Another type had a texturing around 1/8 inch in depth. The spacing of the surface patterns is similar to the size of a nominal ballast particle. The plot on the right shows the force displacement curve from the single tie push test for composite ties and wood ties at 13 mgt. The colored lines are 3 composite ties. As we can see, they had similar or higher lateral resistance to the wood ties results, which are plotted by black lines. Based on the single tie push test results, we had a couple of recommendations in the RIMA manual. The spacing of surface pattern is recommended to be similar to the size of a nominal ballast particle, and we also recommended a depth of 1/8 inch to a 1/4 inch for the surface texture. Temperature is another effect that can affect the performance of with composite ties, especially track gauge. Track gauge measurements using the FRA's T18 track geometry inspection vehicle were taken at TTC's FAST in the cold morning and a warm afternoon of a single day. At the time of each test run, composite tie temperatures were measured at the tie's tops, ends, and sides. The green line shows the gauge channel from the coolest tie temperatures recorded in the morning, and the line shows the track gauge from the warmest tie temperature recorded in the afternoon. 3 composite tie test zones had about 0.2 inch gauge widening due to thermal effect. The drawing on the right shows the general observations that the bottom of the tie tends to remain insulated by the creep ballast. The behavior creates a thermal gradient and generates a center negative bending. Linear expansion of the tie coupled with this bending resulted in a 2-inch gauge widening, consistent between all 3 composite tie zones. No measurable gauge increase was observed in adjacent wood or concrete tie test zones throughout the day. A finite element model was built to further investigate the thermal effect on composite ties. In order to verify the model, the previous in-track temperature and gauge widening measurements were used. The temperatures at the top and bottom surfaces of the tie in the model were set to be 147 degrees and 90 degrees respectively, same as the in-track measurements. Modeling shows a 0.19 inch widening, which was close to the in-track detected value 0.2 inch. The table shows that the modeling results for composite tie materials with coefficient of thermal expansion. As we can see, potential gauge widening due to thermal effects could eat up the FRA allowable gauge widening. CTE could substantially reduce the potential gauge widening of composite ties. We are currently working with Committee 30 Subcommittee 6 composite ties to discuss these results. The goal is to come up with improved designs or guidelines to deal with the thermal effects on composite ties. To summarize my presentation, here are some key findings from the composite tie research, including new guidelines for MOE and MOR based on field tests and observations. We also implemented new ARIMA guidelines for a tie surface pattern to ensure the tie lateral stability. In addition, we developed a fatigue test to address the center cracking issue, and we also found that the thermal effects on gauge may change the FRA allowance for gauge widening. Continue to work with the ARIMA Committee 30 to work on the topics including laboratory fatigue tests, thermal effects to improve the in-track performance of composite ties. In the last slide, I would like to thank the support from AAR's Strategic Research Initiatives Program and the Federal Railroad Administration. Also, I would like to thank UP for hosting the revenue service testing and thank the composite tie suppliers for their tie donation. And thank you very much for watching the presentation, and I would like to take any questions you may have.